Good morning, good afternoon, and good night, depending on where in the world you are logging in to the University of Maine and IEEE AI webinar series. Thanks everyone for joining us. My name is Ali Abedi. I'm Associate Vice President for Research here at UMaine and Chair of the UMaine AI. We are very lucky to have an excellent speaker with us today to talk about AI for power systems. But before we introduce the speaker, I would like to thank our sponsors, IEEE Main Section, IEEE Region 1, as well as our partners and collaborators promoting this AI webinar series around the world, from IEEE in Silicon Valley area, as well as IEEE India and IEEE China. So every first Thursday of the month, we have a different topic. And today, we are very fortunate to have Professor Reinaldo Tonkoski, who is the Haskell Power Professor at the University of Maine and a senior member of IEEE. He has a PhD degree from Concordia University and also have published over hundreds of technical publications in peer-reviewed journals and conferences. Professor Tonkoski also serves as the editor of the IEEE Systems Journal and IEEE Transactions on Sustainable Energy and IEEE Access. He was a peer reviewer for the U.S. Department of Energy's Office of Electricity Energy Storage Program, providing critical assistance in guiding the execution of approximately over $50 million in annual energy storage reach, and also a consultant for the Honolulu Authority for Rapid Transportation project related to voltage regulation. His research interests includes grid integration of sustainable energy technologies, power electronics, and control system. And before coming to UMaine, he was with the Natural Resources Canada and also a visiting professor at Sandia National Lab, where he worked in a variety of projects related to grid integration, renewable energy sources, and energy storage. So if you have questions during this webinar, please post them in the Q&A feature in the Zoom. And after the speaker's presentation is over, we'll entertain the questions. So without further ado, please join me to welcome Dr. Tonkoski to the meeting.
Thank you, Professor Abedi. I really appreciate the introduction. And I also appreciate, I see that a lot of familiar names from South Dakota in the audience here. So some students, to Kate here, some familiar names there. So I'm really happy to touch base with my old institution here too, my colleagues there. And a lot of what I'll be presenting today has to do about the work we started there, and we are bringing and creating this exciting new power engineering program at University of Maine. So I hope I can share about today a perspective from a non-AI specialist, actually, and what are the opportunities that are out there for us to solve and address these major issues that we have in power systems. We also often refer that to the interconnected power system or the electric grid as one of the largest and most complex machine that humankind like we ever built there. There's a very complex interdependency between different parts of the systems, not only in terms of fuel sources, but also from the control structures. Whenever things get wrong there, in the planning, the operation, or control of the system, that creates a lot of issues for us. So as you can see here, one of the things that comes to my mind, I think, that was very impactful, especially in the media there, that 2021 blackout in Texas. That in that blackout alone, about 4.5 million people and business were without power. They were 4 minutes away from a complete blackout in the system. So that's how far they get. 4 minutes in power system, it's pretty close to collapse, And to get back from a complete collapse of the system takes a lot of days and a lot of resources to get it back. Just even without reaching there, the cost implications were huge. We had about $195 billion that were estimated that that blackout cost. Worse than that, we have actually 151 people that died. So many of them directly or indirectly just because of the blackout, because of the cold temperatures. So as power systems engineer, we are always striving to try to avoid those things to happen and create systems that can avoid those the impact on our population. So I'm going to be talking a little bit about what are our challenges here, especially talking about our goals about reducing our emissions as well as improving our resilience in the power system. That will be my main part of the topic, and trying to focus on some areas that AI can very easily provide solutions for us to address and be very impactful in our livelihoods. So when I talk about emissions, isn't it? I'm going to try to give you a 101 in electricity generation, electric power systems, and what are relevant things that we have been working. So as we know, we have a lot of mandates around the country and worldwide to try to reduce our greenhouse gas emissions. About 50% in the US of the generation, even though we have made a lot of efforts, they're still fossil fuel based. We're still generating a lot of greenhouse gases. Even though we had done a very strong, we have improved considerably by shifting from coal generation to natural gas, which is slightly cleaner, energy source. So that gave us some gains in terms of emissions. So we're not polluting as much due to those things. We also integrated a lot more renewables than we had in the past. Still, fossil fuels is it's the big generation source, and actually in 2021, actually we can see that the emissions are still growing, and that has to do because people, they need electricity now more than ever. So our electricity usage is still growing, and our fuel mix that we have supporting that is still not as clean as it should, so to be able to support these emissions. And that's actually a very complex problem to solve. It's not only about adding renewables. We have a lot of, let's call it, greener states versus non-green states where you had a lot of emphasis of using renewable energy integration. California is one of them that's always pushing the bar there to try to get more renewables, and you can see in the system, if you look here, the electricity consumption, most of it they have very low emissions in that area. But the problem is that in power systems, we have everything is kind of interconnected. Okay, if you look here, our large power systems is typically divided in the Western interconnect, the Eastern interconnect, and then we have Texas all by himself here in the South. So you can see that whenever we have shortage or needs from electricity from one place, typically the economical way to do it, we try to get from somewhere where you have access to this electricity. So when you have a ton of renewables in California, and at some point, if their renewables are not being able to meet all the load demand, we are going to be importing some electricities there to try to tackle those moments. And you can see that you will start emitting greenhouse gases somewhere else, and this math is very interesting because it shows a little bit the granularity and the impact of this problem. You can see that generation, the electricity consumption, and carbon emissions is it's quite correlated in the system. You can see different market entities here. Especially in this Midwest here, where you have a lot more, still a lot of non-renewable energy sources. They are the ones that are generating more consumption. So we have to address this problem. And so at sometimes it's all about load shifting or replacing the energy resource for a cleaner one, or trying to use energy storage. So we need to figure out a better design in our system so that we can avoid those global emissions. Also, we're talking about climate change and the impact of those emissions, and we are having more frequent droughts. So which means that we're not going to have enough hydro generation anymore as much as we had in the past. So we might have periods that we are going to lack hydro generation. So we need to compensate those things for something like that. Otherwise, we're going to run out of power at some point. Extreme weather events, outage. So we're starting to lose large areas more often because of extreme weather events. Just in 2015 to 2020, we had about 60% more blackouts in the United States, and that annual cost is about $150 billion, just those blackouts. So those are major issues happening. Here in Maine, just to give for our local people some information, it has been often in the news. You can see that those extreme weather events, they are driving major outage here in Maine. We are very vulnerable to winter weather, hurricanes, extreme heat, and wildfires in the region. The last 2 days, we have about 53 major weather-related events here. And you can see that in the last 5 years, we have a lot of increase in those events, in the number and the impact of those events. We have one in October 2017. We have about 500,000 Mainers run out of electricity for 3 days and have major implications here. More recently, in 2023, in March of this year, we have 250,000 people in New England without power. And it's interesting, when we moved here, we start seeing that a lot of people here have backup generators. So there's an added cost for us that's affecting us. So we need to build up our resilience in our households to be able to handle those issues that are happening elsewhere in our electric grid. And this ISO New England is our major authority here in the region. They are very, very concerned about what is going on around here. Especially, we are converting a lot of our heating to natural gas, and if we start using a lot of natural gas, you saw before in that slide that the electric grid, they need that natural gas. So we are gonna be paying some higher costs probably for using it for electricity generation, and or at some point we might have shortages that are going to create major issues to handle the power system. So this interdependency between different sources of energy, it's a major issue in power engineering for us to handle. As I was mentioning, like, it's affecting our pockets here, those things. If you look here in Maine, we're one of the states with the highest energy burden. While someone might be thinking that this slide has the intention to try to increase my pay here at the University of Maine, it's just to bring some awareness. I was really shocked here about the cost of not only electricity, but the fuel here, that we're, especially during the winter, it can be pretty substantial. Just my house, I spent, I think, about almost $1,000 per month in the peak of the winter here. That was kind of scary when I arrived here. So those things are major issues that we're trying to solve. How do we integrate more renewables? We convert the power system to be greener. At the same time, we maintain affordability so that people can do it. And the good news here for the region is that we have a very high potential to grow offshore wind here. And so that's very exciting news for us, that we have a clean source that can be tapped, that we haven't been used. So which means there's a lot of potential to grow in the region to address this issue. So let me dig in a little bit about what are the technical challenges related with this grid decarbonization. Okay, so if from power engineering, we are replacing some sort of generation. We're replacing those natural gas and coal generators by renewable energy systems. Those renewable energy systems, they are different from that non-renewable generation. The old or heritage system, let's say, what is online right now in terms of natural gas and coal systems, they use very large machines, similar hydros. They have very large machines and motors there that we control their frequency, or that rotation there, to maintain the frequency of the grid. And that's how much we also use that as a way to maintain the energy balance, controlling that speed of that old generator there. What's different now, when we start having more wind energy systems and PV systems, those sources are different. The interface with the grid is not anymore a very large machine with a ton of mass or inertia. That's the technical term that we use in power systems. Those coal generation and natural gas generator, they have very large amount of inertia that helps us to control and keep the system stable, Renewable energy source, they don't have that. They are very fast. So that changed the behavior of my system. I have now, I don't have the same unit in the system. So my models also, from what I used to worry about the power systems, they are not the same. I cannot use the same model of a co-generator to represent a wind energy system or a solar system or an energy storage system, even though the power, from the power perspective and the energy perspective, they look very similarly. Dynamically, they are completely different. If you didn't understand anything that I said before, I just want to use an analogy here. This is what we have now, okay? This big guy there trying to winning the Olympics here because they can hold a ton of weight there. They have a large mass. So if somebody pushes him, nothing is going to happen, you know? And we're replacing the system now with Usain Bolt, you know? That's what we're doing. If you think about Usain Bolt, that's solar, okay? He's even wearing the a yellow shirt to remind us about solar. That's one of the front runner technologies that is coming about renewables. And we have our other renewables coming in the back. So as an aggregate, renewables are very relevant. They can address a lot of those issues very fast, and they can have a major impact, but we need a lot of them. And we need to have coordination on that to be successful. And we replace those big, larger power plants with those renewable energy source that we have that are just more modularized. And when we did that, okay, when we start replacing, we thought that we had a very nice design in place. So as power engineers, we can get very accurate models from each one of those sources. And then you can see that we start having a lot of renewables in the California area. But we start realizing that even though we had a very nice plan to maintain reliability, and we created a lot of functions in inverters to happen, we're still having some things that were happening in our system that we couldn't explain. So NERC is our entity, is a non-governmental entity that keeps track and helps maintain the power system reliability. They start investigating those events and trying to keep track about what is happening, how can we solve. This is one of the latest reports from NERC about some disturbance that happened in California. It's a very interesting document because it shows that it gives us some messages in the power systems planning that we're not there yet in a robust solution to maintain the reliability in a very high quality standard in power systems. One of them that we learned was that our models that we were using for analyzing the impact of large scale, like those utility big solar plants. I'm not talking about or residential solar PV. I'm talking about those very large PV that you have interconnected in the utility system. Our models that we were using to study whether they were not matching what was happening in the system, and that's a major issue here. When you start having our models that you're planning, the system's not matching. So some solar plants, they were disconnected to the grid when they were not supposed to. When I lose generation when I need it the most, that's an issue because that's create those tripping events that can create cascading blackouts. One of the challenges to handle this is because solar is coming slowly to the system, and we have old solar plants versus new solar plants. We have an inverter manufacturer that went bankrupt, and nobody knows what's inside those inverters. So we don't know the settings. We don't barely know some of those details. So we have those old heritage systems with new systems that we and in the new systems, even though we might have access to the manufacturer, there's a lot of IP related to those inverters, and the manufacturers, they would not simply release all the details about how they implemented those functions and how fast they are and all those details. So there's a challenge in modeling here that we have now in the power system that we're addressing. We are also noting, we remember when we talked about that big guy versus the fast guy. We're seeing that in UK, for example, we have a lot of wind interconnected there. And we have a couple of generator plants disconnected. They were wind source. That was what they were looking at. It lasted about 45 minutes, this blackout. But this actually, everything, if you realize what is happening here in the system, happened in less than a minute. Okay, so there was something happening in the system that tripped those generators that created this very large frequency deviation, and that triggered an event that disconnected a lot of people from the power system, and that generated a blackout. And those large frequency events, so that's the variation, the frequency. So thinking about electricity, AC systems, you can represent your voltage source by a sinusoidal waveform, and that's we look whether we have good power quality, whether that amplitude of that sinusoidal is adequate, and whether the frequencies within that those acceptable boundaries. Those are the two main parameters that we look in terms of power quality. So when things go out of bound, if my voltage is too high, or if my frequencies start to deviating too much, there's something wrong. So there are protection schemes happening, designed for tackling those things. And this is what happened in this event here. So the protection scheme found there was some issues here, and we didn't have anything to counteract and to keep that frequency in acceptable level. So the system tripped, and a lot of people were out of power. We're also dealing with different types of parameters now. With the electrification of the transportation systems, it's creating different dynamics. So I was lucky to work in this project from the Honolulu rail transit system for related voltage issues. When you start having a lot of electric trains in the system, especially in a weak system like in Hawaii, where you have where you are in an island that doesn't have the same strength as the big power system. Those very large power variations, they have a different impact. The power system becomes more susceptible to those variations. So this voltage, it creates some voltage changes that can create some major issues for your loads. And correlating what's going on in Hawaii about solar integration, that's very challenging to keep the power quality of the system up, because the voltage band that they have to keep the system range start becoming pretty tight. And if we don't have solutions for these problems, okay, that can mitigate impact, we are going to be paying a lot of large price tag here for all those projects. So we are talking here, they need to install for this transportation project about STATCOMs, and that's a solution that's expensive, about $150,000 per MVAR. So which means that each substation will be costing a few $1 million more because of those voltage issues that are happening in the system. So can we design systems that are better to tackle those that can mitigate this impact in terms of the energy burden us and can help our loads be interconnected safely? That's really one of the big questions that we have in power systems. So you see that I have pretty much half of my presentation about power systems, but how AI fits into this game it's a big question here, isn't it? A lot of things that are happening has to do about this difference in behavior. So speed is something that has been a challenge for us to deal with renewable energy technologies. We need things faster and more precisely than ever for power system modeling, control, and operation. So there's a lot of need in terms of load forecasting that you see very large initiatives from DOE trying to improve forecasting, load and weather forecasting for renewable utilization. The other thing that we are looking that we discussed a little bit, we need better models that are precise. And precise now it's very difficult to address, because my generation source now, it's always changing. Renewable energy technologies like solar and wind are somewhat recent. They start becoming more and more power electronics oriented, which means they have more electronics than we ever dealt with in the past. That brought some very interesting and cool characteristics for us to work with, but it's still something evolving, so it's changing all the time. So how can I design? How can I develop models that are flexible? That we don't keep chasing ourselves all the time and trying to update our models so that I need to learn again everything that's inside those units to be able to make sure that they are precise, and also that's not that complex that I cannot compute timely enough, because a model that you cannot that gives you the result before some event happens, there's not much use, isn't it? It's like you're not gonna a model is just as good as it helps you to make the right decision at the right time, isn't it? If it's too late, hey, you lost your opportunity. to be helpful. So speed is a major issue here for modeling. Same thing for control systems. We need faster and optimal and secure controller. State estimation is a different challenge because we're trying to measure now parameters that are very fast. So one of the examples is rate of change of frequency. So we used to monitor a lot of frequency, but now we use a lot also the rate of change of frequency, which is the derivative of the frequency. Every time we are trying to measure the derivative of something, it becomes very challenging because anything that you have in terms of noise in your measurements is start to impact your output. So we need better filters and filters that doesn't affect the bandwidth of the system. Okay. We also need a lot of highly granular, precise load management. That's very important for us in the power systems. And cybersecurity. I could spend the whole day talking about each one of those applications, but we tried to pick a few of them that we have been working to give some examples about how AI can be helping us. Okay. So power systems engineering we are very conservative people because of the responsibility that we have in hand, as you saw, to tackle this. So AI has been in one of our tools for us for a while. We have been investigating this, but it has been very challenging to deploy in a way that that we can make something that's very resilient and very and we can trust. I think the big issue in the AI has been about the trust. Can I trust that a decision will be the right one in the right time? So this is something that we are striving to find that balance. And we have been improving substantially the utilization of AI, especially every utility now are starting to hire computer scientists and data scientists to try to address this area. And once in a while, I have people asking me, "Hey, how do we start to put together a team here?" So in the right way, so that we can use our data that we have available to improve our operation of the power system. And if you look here, the AI community, you guys know all about all the state-of-the-art methods, and they are very capable to solve a lot of our biggest challenge. The big question is always, hey, give me the data, isn't it? That's one of the big challenges that to integrate AI still to today has been a challenge that utility has to deal with a lot of data that has a lot of security and proprietary information. It's similar to the health system. You can't simply share easily that data. We have major concerns about privacy concerns, and also about how that information can be used in terms of security. So we have a lot of data protection things in place to protect that. But this has been something that has been delayed, the application, the utilization of AI in power system substantially. And this has been a radar for many years. We actually wrote a paper in 2019, a little bit, actually, we started this paper in 2017, I think. We got together a bunch of researchers with industry people and national labs, DOE officers, and we tried to look what were the opportunities at that time in terms of using that data, and what are the biggest challenges and opportunities and future directions. You see the key challenges that we identify in this paper. We found as data volume, data uncertainty, data security, time synchronization, data indexing, and one of the big ones, standards and regulation and data in the utility industry, they were not there. And it's still not there. This is still one of the big challenges that we're trying to address here, to the point that the White House recently issued this call for real-time standardized and transparent power outage data. It's interesting that we have no idea about how often these outages are happening and how big it is, at least in the public level. So even for us as researchers, it's very difficult to have access to this data to be able to analyze how big is the impact in the system and how could I improve the performance of the system. So there's a lot of initiatives going on now. So you're going to see in the next 3 to 4 years, for sure, you're going to be flooded with data to have fun from the power systems community. Actually, not only from power systems, we are learning some big industry players operating from telecommunications, cable companies. Actually, they have a lot of voltage sensors deployed in their systems, and we are learning how to leverage those other sensors that we have in place for other applications, and how to help monitor the power systems and get better data for us to analyze the impact of blackouts with higher granularity. But then becomes the challenge is always the time synchronization of this data. So there's a lot of initiatives coming to help get AI powerful. Within this data framework, we have in 2017, if I'm not mistaken, 2019 actually, we put together a team to address the modeling issues that are happening in the power system. We got together with University of Alaska Fairbanks, University of Puerto Rico, Mayagüez, HD and EI in Hawaii, National Labs, Sandia, and NREL are great players with us, so that we can improve those models and avoid those things to happen. What we learned in this project, okay, the big framework is that we have within the power engineering community, we have two different separate communities. One of them here are the people from power electronics, the people that are designing those inverters that you use for your solar or for your wind generator, and the people that are setting up those the electronics behind it. So we are very good actually modeling. That's one of our strengths. I'm from power electronics perspective. I came to power systems from the power electronics community. So we have a ton of tools that we get very precise models that can represent things at the nanosecond level. So precision is not an issue for us, okay? And from the power systems communities, they are very good in modeling, but they tend to see the system as an aggregate, as a big picture type of thing. The problem is that their models are very good in the seconds level. So if something starts happening from inverters that we're designing in the microseconds level, those models, they fail completely. They don't work. But when we are thinking about representing a power systems that would have like thousands or millions of customers in there, and you need to have accurate models representing this generation consumer prosumer that we refer here, the consumer that also generates electricity, interactions to the grid. Those models, they become, if you use the power electronics model, they are going to be computationally intractable. We are not going to be able to solve those problems in time. And from their perspective, the power systems models that we have been using, they're not accurate enough to predict the system. That's what we have been seeing. So our team has been working in South Dakota State University, University of Maine. We have been working in those data-driven modeling techniques to try to bridge those two words, you know, about trying to find a model that's accurate enough for helping you making a decision, at the same time is capable to define the right, to make you do the right decision the right time. So we have been exploring a lot of those data-driven modeling techniques in this aspect. Okay. So this is one of the examples of projects that we have been using. And when we're thinking about AI and controls and data science, so we're a very tight community that we work together. And there are some methods there that we started investigating. It has to do a lot from the control systems community here. One of them we have for modeling to try to get models from systems that we don't know much what is inside, so we don't have a lot of knowledge about what is inside that inverter. We have an idea. We know what's the template of that model. We know what it resembles that transfer function, but we don't know exactly what are those gains and that are inside set up in that system. So we started developing these techniques, offline and online techniques, that they have different applications in power systems. One of them is using linear and nonlinear system identification toolboxes that have been available for a while, where we would excite the system with a signal and analyze what is the output and try to infer the model, the coefficients of that models. And those linearized models, they would be technically have a better fit than those templates that when we don't have a good knowledge about what is inside that inverter. We have been also using some online filters to solve the same problems. Sometimes we are not only thinking about the model inside the inverter, but we might be also looking to the aggregate of the power system, how to represent this grid interconnection, the short circuit capability of the interconnection of that renewable energy source to the grid. So we might want to estimate some parameters like the R and L from the circuit, for example, to try to improve controllers. And this type of process needs to be done online. That's for voltage regulation. So this is one example about how we apply this model and how do we collect data for this, because I think data is typically, for me, the biggest challenge here. So we developed this experiment here where we get a solar inverter, okay, or we could do similarly in a big solar plant if you have this capability of large energy storage units. We go to the solar plant and we excite this inverter under different frequencies. And by doing that, okay, so we use some sort of probing signal, and can use their large variety of probing signals that you can use. And this is actually a research question that we are trying to figure out, is like which one is the best one, probing signal to extract system dynamics from inverters or other renewable energy interface to the grid. So we start investigating by using this probing signal, and we start develop this method this new methodology to do models where we represent those transfer functions under different regions. So we have linear models that are valid for a very small range. So very similar if you are familiar with small signal analysis. That's what we are doing in this case. We're doing small signal analysis in a different level. And later on, we aggregate those models. I think it gets a little bit more clear with this figure. So in an inverter, we developed this test protocol where we would slowly creating this chirp, the square chirp function here, and exciting the system slowly for different ranges here in terms of voltage. So we start slowly increasing the voltage. And later we analyze this data to try to obtain their models, okay? So we obtain different models using different probing signals in this case. And we actually got pretty good results just by doing that. You can see that most of our models are matching our data. And this is like the training data that we use there. And everything was above 90%. So those models has been very showed a lot of potential for modeling inverters. What is also interesting that happened here, when we were setting up this experiment, one of my grad students, he was setting up the inverter, and he didn't understood well what was the setup for the voltage thresholds, or which means when this control here doesn't work much, and where you start having these ramps here. And we noticed that we couldn't identify those shapes, this steady state behavior here very clearly. So there's a lot of potential also about those techniques to do to assess whether the solar plants have been set up in the right way. We don't know. We just at this point, the way that we evaluate whether those solar plants they have the right settings is like we go there and check the settings manually there, or someone goes there and evaluate, or we just trust someone that they did a good job. But there's no double checking. We do some experiments once in a while about the interconnection process, and we try to monitor the data to try to identify whether there's something wrong, but there's no formal procedure. So this type of methodology to extract data can have a lot of potential here for us to identify issues before something really bad happening into the power system. What is the drawbacks of this method? So we solve all those problems with control theory, isn't it? Like some basic thing. The problem is that this methodology that we put in place, it's still, you see, linear systems. And I'm giving them the template of the system dynamics of that transfer functions. And the problems that this generation makes, the characteristics is it's really changing. We don't know how much is going to change. Now we're talking about controllers that are using things that are completely nonlinear. How am I going to represent those things now? So we need new tools, to be implemented within to obtain these models that are capable of adapting this model better. So we should have like methodology to extract data and create those models based on this data extraction process. Otherwise, we are going to keep forever chasing our own tails. That's how we feel in the power engineering community. Finally, we develop a model that it's very accurate and very nice, works for these renewables. But now what happened is that, hey, we changed now. We created a new advanced grid support function that's going to help the grid get stronger. But now, hey, my old model doesn't work anymore. So I need to have something that's more sustainable for the community to deploy new system and with a good and maintain good accuracy with those changes, you know. So deep learning method based models have a lot of potential to address this, and we have been investigating those possibilities in our system. The other applications that we have been looking at is for dynamic state parameter estimation. The difference between states is like state we're talking about what we're showing here as the angle of the voltage this is the frequency of that voltage, and this is the rate of change of frequency. This is the derivative of that of the frequency signal that we have there in the power systems. And the big challenge there is because we have new control methods that depend on those signals to make the right decision at the right time. And this needs to be done in millisecond range. So what happened is that we need something that can clean the noise for us and just give you the right information. And we have been developing this. We have been using moving horizon estimation for this and common filters and things. And each one has their own issues. But the bottom line, I still need a model to be able to filter this. So how can I handle a new model, a new dynamic state estimation methodology that I don't depend on really knowing that well the system dynamics, you know, beforehand. Even though they have a very good result. So when we develop these techniques, the big issue is really that those systems are changing, and I am pretty dependent in the models. So we have been exploring at this point something to avoid us again to chase our tails, you know. So reinforcement learning here has a lot of potential for us in terms of improving this dynamic state estimation process and ensure that we have a more sustainable way of dealing with these signals and push the boundaries here. Similarly here, we do one of the parameters that we keep. Remember, I talked about the big guy there versus the Usain Bolt there. We need to keep inertia measurement pretty in line in the power system here, because otherwise you start having those large frequency swings. So inertia estimation has been a very hot topic in the last 5 years, especially when you have multi-area in the power systems. This inertia, it's pretty much area dependent. So if you have a different area of the power system where you have clusters of generation, they might have a slightly different values because they might be more preeminent for frequency variations than others. So how I do that, that's a big thing that we have been looking at. And this is something that we came up, our team at South Dakota State University and myself. So we came up with this inertia estimation technique based on convolutional neural networks and federated learning. So the convolutional neural networks makes the local inference about inertia for a certain area, and the federated learning start addressing those variabilities, this local variation, and how that impacts the global inertia value. So the interdependencies between that those tie lines between one area and the other area, it's addressed based on this federated learning approach that we have in the system. We also been developing some applications related with control systems. So our controllers are getting faster and faster. And what happens is that frequency dynamics in the past, we wouldn't care that much to milliseconds things. We would care more about second events. Now it's starting to get the boundary of frequency events starting getting closer and closer to a millisecond range. And when you start doing that, there's an interdependency with the voltage dynamics that is the faster dynamics that we typically have to handle it. And that's very similar to what's happening in the Honolulu rail transit system. My voltage support there, it needs to be something fast that can address those fast variations from those electric trains. So what happened is that when I start doing the best control methods that we came up is that we need to, for example, in model predictive control, we ended up looking into a window that we initialize when we have this dual time constants that we have. They're kind of close together, but they're not at the same time. Typically, you need to pick the value of our time horizon window based on the slowest dynamics, and the sample time is based on the fastest dynamics of the system that you're trying to control. When they are too far apart, when you start having too many data points to optimize there, and that start to become very large, and you become unable to solve these problems in real time. So there's a big challenge of now how can reinforcement learning support this type of activity. So for example, we have developed this moving horizon estimation NPC framework for doing frequency control in the system, and it works very well. We show that we can get very optimal control decisions. We can actually adjust. If I use an energy storage system to try to support the grid in terms of voltage for frequency control, we found that we can reduce that. You see here that when we're seeing here this blue curve here, it means that our frequency deviation is it's lower in this case versus the other. So I can actually, with this framework, I can change the settings. So this is if I don't have controller, but if I just change a little bit the control settings here, I can get more service, better frequency regulation, and lower. So I can adjust my quality of the services. And here is for rate of change of frequency, or the derivative of the frequency. We can do the very similar thing, and those are parameters that we're using in power system protection to avoid cascading events. So we can, if we develop those good frameworks that are happening very, very fast, this is something has a great potential. We did also similarly for voltage support, and we showed this very good behavior in our system. But the big problem was when we integrated both of them together to try to address those two problems that we have, this input coupling issue. Our simulation, our solution time just in simulation was taking 17 hours. So 17 hours to make a solution for something that needs to happen in 1 millisecond, that's not a good solution, isn't it? So what we have been trying to address here, we are developing this combined methodology where we have a model predictive control that is still have an excellent performance, especially when we talk about frequency control, flexibility. And we're trying to use this supplementary controls, the reinforcement learning agent, to try to support better the voltage side of things. So that very tiny part of the time step is being learned through the reinforcement learning agent, and then we make the control decision for the fast frequencies using this unit, and this unit keeps at least the frequency dynamics more optimally close to the reality. So with that, I kind of gave you a little bit about some ideas in terms of decarbonization of the grid and methods that we need. What are the big challenges that we as researchers in power engineering that we're tackling related with modeling, state estimation, and control systems. And some ideas for us to try to recruit some people from the AI community to help us solve these challenges. So there's a lot of opportunities for AI researchers, which will require a lot of talking with power engineers for us to find common ground. We need to speak the same language to develop good solutions. There are a lot of limitations in our area that typically we handle, and most of them relate with data, with all those relationships in terms of data privacy, data synchronization, and many other aspects, and also about computational resources to implement those solutions has been one of the challenges that we have nowadays. With that, I just want to give an acknowledgement to all PhD students from South Dakota State University, University of Maine, also that has been participating in this research, especially to Niranjan and Asta. Niranjan actually should be the one presenting doing this presentation. He's our AI expert in our group, has been an amazing job in here. Asta is also doing an excellent job in the modeling aspects here in our team. And I cannot forget to thank our sponsors from National Science Foundation and also U.S. Department of Energy through their multiple programs, especially this grant that we have in collaboration with multiple institutions, has been very helpful for us to tackle those big challenges that we have in front of us. With that, thank you for listening to me. I hope we still have many of you awake here. So I'm glad to continue conversation.
Thank you very much, Dr. Tonkoski. This was a very interesting presentation. We asked the participant to post your question in the Q&A. feature in the Zoom, and we'll go over them as they come in. So the first question is that what will be the frequency of the probing signal, and what is the strength?
I can give you a very clear answer, an honest answer at this point. I don't know. Well, let me explain why I said that. We're experimenting this actually because we're trying to learn what are. Let me come back here to this slide here. We have an idea about what are the frequencies that we're interested to develop a very accurate model there. But at the same time, to get the most accurate model that we have, sometimes we are seeing that if I expand a little bit the search space, or if I do some tweaks in the shape of my probing signal, I can get good advance that I don't need to, that I can get better estimation, better accuracy at the end. So this is actually a research question that we have been looking into, how to define that frequency. Not only the frequency range that you should set, but also the amplitude. From power systems, we don't want, especially if you're probing the power system, and we're running some experiments with Sandia National Labs to probe a whole microgrid. So we're going to put an energy storage system there. Well, they already have an energy storage system, but we're going to probe that signal. We're going to create this signal. We're going to inject in the microgrid and try to extract the frequency dynamics of that system. When we do that, we don't want to do a frequency variation that's too high, because otherwise the system is going to trip or create some cascading event. So yeah, this is a good question. So typically we start by looking at what is the frequency that you're interested in having a good model at, and start from there. And later on, we're still researching this aspect.
Great, thank you. Next question is that, is there or will there be a testbed grid to evaluate AI models versus traditional?
That's a good question too. It's like there are lots of benchmarks there. The national labs have been doing an amazing job in trying to deploy those test beds, IEEE, in collaboration with IEEE. You have, from models perspective, we have a good one. From data, I think, if I'm not mistaken, it's DOE Better Grids repository. They did a very good job there, deploying a lot of data sets for us to play with and try to analyze for energy management. So there's a lot of things available. The question is typically like where to find the right data. That's a real big challenge that we have in our system. But yeah, there are lots of available. If you need something particular, I'll be glad to try to help locate it.
Thank you. And the next question is that, could you discuss use of AI in managing energy storage, and what are some of the issues?
So I think, instead of answering precisely your answer, I'm going to refer this, I think, in terms of AI, Sandia National Labs is home of the energy storage program from the Office of Electricity. They came up with the energy storage handbook. So if you just Google energy storage handbook, Sandia National Labs, you're going to see that there's a new publication out there that has been released this last year or so. There's still new chapters coming here. It's supposed to be a live document that are coming up, where you can have a lot of information about that part of about energy storage. In terms of the AI side of things, there's a lot of applications about how to dispatch, how to coordinate when you have a lot of distributed energy storage in the system, especially when we're talking about providing voltage and frequency support. And this coordination becomes more important to avoid the power system to collapse. So this is one area that I have been very active looking at. There's also a lot of opportunities related about the participation in the market, how to use your forecasting tools to operate energy storage in what we call energy storage arbitrage. Is when you buy and sell electricity. You buy cheap electricity and try to sell it when it's expensive in the system. So those are some of the things that I can quickly think about related with energy storage systems.
Excellent. So next question is that, are these models useful if you can detect failures but cannot predict them, and or is there input that allows you to predict with enough time to make useful changes to prevent the grid shutdown?
That's a very good question. I kind of we start seeing about this potential of those models about identifying issues recently. I have to be honest, I suspect that we have a lot of issues in the power system settings that we don't know because we don't have a way to verify and validate. And we just validated there was an issue when something bad happened. Then had start falling apart. So that's a good point. I don't think we have done enough research in this area to tackle and to find ways to leverage the capability of those models or the value of those models in the long term. So that's something that we would like to explore at some point.
So before I go to the next question, I also have a question myself. So I just inject this in here. You mentioned in one of your slides that it takes 17 hours to do that training and simulation of that. Does that include the training part, or is it after training?
So that was just pure model predictive control approach. There was no training involved. So it was an online method with the estimation and the control framework. That's one of the biggest challenge in there. And there was a lot of settings that we are figuring out still with NeuroJohn. So NeuroJohn has been the one tackling this problem, trying to interface the reinforcement learning. So we are hoping that in the next iteration that we can show the results, that we can we can bring this to real time soon. That has been our challenge this semester that we're tackling.
So basically, if you finish that reinforcement learning process, then maybe the model can be configured for the more real-time, effort later on. So okay, that was
perfect. And then the big question comes like, how do I generate the data? Because we can train models based on models. So how do I create a data set that will be very representative to what will happen in the grid, that I can do a very good job there? That's something that I think we are learning how to do that in an effective way and efficient way too.
Great. So we have 2 more questions and 3 minutes. So let's say try to address both. The next question is that, could you talk a little bit more about how power electronics can mimic a rotational generator, and what are pros and cons and the AI tie-in?
That's a good question. So this area of research in power electronics, we call it like virtual inertia, or what I like to call it fast frequency support in power systems, because virtual inertia, yeah, it refers to inertia, but our concern is about frequency, okay? So we came back pretty strong in the last 5 years with solutions in that area. We created some topologies that we called now, we're calling them grid forming inverters, where they have these embedded inertial characteristics of those traditional generators. So we can mimic that inertial response in the power electronic side. There is still some questions here that haven't been solved in that aspect. So let me rephrase here. We can generate inertia with power electronics based systems. The big challenge here is like, can it keep the system stable, or there will be control interactions between those units that are going to create some instability in the system? That's something that we are trying to figure out, and we're trying to make demonstrations also about at what level that happens.
And the last question really quick is that, do you adjust models for all different types of renewables, or have you focused mainly on solar? And will you need different neural nets for each type of renewable?
Yeah, that's a good question. So we have been working mostly with solar and energy storage. Those are the 2 first test cases that we did. What I can tell from the power electronics perspective is that renewables in general, they are very similar in that aspect in terms of the topology-wise. Let's say the template is not terribly different. It's going to be one is faster, one is a little bit slower. It's going to be a little bit maybe some will have some different functions integrated into this. But yeah, so we haven't yet done research with wind energy, for example. We have done most of our work has been focusing on solar and energy storage. As you can see, there is also a source of funding. So that's one of the reasons why we kind of focus in those 2 technologies for now. Great.
Thank you very much again. We are out of time. I just want to thank our speaker once again, and thanks everybody for joining us, as well as our sponsors in IEEE in Silicon Valley, in Region 1 Northeast USA, IEEE China and India, as well as Maine section and also University of Maine. Thanks again for joining us, and please check out our AI webinar website later on for future events, and have a great day, everyone.